types. Yeah.
Okay, so the last talk of the day is by Takeshi Morita from Shizuoka University on bounds on chaos and acoustic Hawking radiation in free Fermi fluid.
Okay, so thank you, Manas, for inviting me to this beautiful place. I took this photo at the lake near this institute, and I love this beautiful location very much. And I'm also from this high energy community people, so I'm very I'm enjoying this conference, which I can learn a lot of stuff from some various topics. Okay. Yeah, it's working. Yeah, and this talk is based on this archive, and so on this talk, I like to discuss about the bound on chaos. This is proposed by Mardashna Schenker Stanford at this 2015, and the claim is as follows. If we consider some many-body system at finite temperature, and then the Lyapunov exponent would be bounded from above by this temperature. So this is a conjecture, and they under some suitable assumptions, they prove this bound exists. And so maybe many of them know this Lyapunov, what is this Lyapunov, and so on. So, but I briefly explain. So if we consider some dynamical system and change the initial initial state a bit, and then this deviation develop exponentially with time by this factor, and this is called Lyapunov. And so the reason, so these are also some kind of high energy people, and the reason for why they consider this kind of bound is related to radial shift correspondence. So according to them, the situation at which this inequality is saturated is some kind of quantum gravity system. So one example is some black hole system. Maybe this is related to the previous talk by Gautam. And also this so-called SYK model also saturates this bound. And then people claimed that this saturation means some kind of the system is most chaotic, or it maybe represents some fast scramblers, or a kind of signature of quantum gravity because this is related to some kind of black holes. Yeah. Yeah. In quantum case, more correctly, they define this Lyapunov by using so-called OTOC, that is related to Manas's talk. So they consider some kind of 4-point function, and it's a sort of some quantum analog of this kind of relation. And so that is
in what time interval is the growth exponential?
Sorry?
So you said short times. What does short times
short time.
mean?
So it's
what does that mean?
So yeah, typically this is this time is less than so within the Ehrenfest time. So usually it's so typically so maybe even this model shows some exponential growth at the first stage, but later it would be saturated because of if the system is closed as usual. So yeah, so this is just for some short time. Yeah, thank you for the question. So okay, so the reason for this relation may be interesting is so this relation connect chaos and quantum gravity, and both are very important topics in theoretical physics. So maybe this bound may be interesting. Which one? This one I brought from my Mathematica, and this is I will explain later. And this is I don't know some from Wikipedia. So sorry, and maybe for this talk it's not nothing. Okay, and so this is some inequality, and this relation I can rewrite in this way. This is completely the same relation, but just You see, this is the same equation. And this inequality says that the temp, we can reinterpret this relation in the following way. So suppose we fix Lyapunov exponent, then this relation tells us that the temperature is bounded from below. And this is something about this relation, but today I like to focus on this relation, and especially I like to explain this relation may be very interesting when we consider in some semi-classical regime. So today I'll discuss only some dynamics in semi-classical physics. Okay. Yeah, yes, that I will explain later. So, but it's just, so this is, okay, I'll explain. No, so that is the point, and that would be some very interesting point. That I like to emphasize today. So exactly, so your question is my starting point. So I'll explain why this inequality is interesting. And so this is some picture that is some classical motion with some finite Lyapunov exponent, and the temperature is 0. And this is a standard situation that we are considering chaos in some dynamical system. We usually do not putting in this temperature. So this is a really standard situation for the study of chaos. And suppose we turn on quantum correction to this classical motion. So then, if we believe Maldacner's conjecture, these inequalities are satisfied. And so these are the same inequality. But so then we have two possibilities. So now we are, this h bar is non-zero, but maybe it will be small. And if this is true, and so initially this lambda is finite and the temperature is 0 at the classical level, and the question is what is going on at the quantum level. So we have two possibilities. So if we look at this equation, so and suppose we assume since this is temperature is 0, it means this lambda is bounded to by 0. So the one possibility is in quantum mechanics, this Lyapunov becomes 0. And another possibility is if you look at the relation in this way. So now this Lyapunov is finite, and then although the initial temperature is 0, but maybe the temperature is bounded from below. So we have two possibilities. And so the question is which one is realized. And the point is we are now considering in some semi-classical regime, it means the h bar is very small. And at the classical level, this Lyapunov is finite. So it means this first scenario sounds unlikely because once we turn some small correction, this lambda suddenly becomes 0. So then this second possibility will more likely. I mean, in this inequality, the right-hand side is some small quantity because h bar is very small in semi-classical regime, but this and this Lyapunov is some finite value. So it means naively this may be occur. And if this really happens, that sounds very interesting in the following reason. So this story reminds us some black hole physics. So in black hole, in general relativity, this is just a classical solution of Einstein equation. And it means this object is nothing to do with thermodynamics. However, we know that once we turn on quantum correction, this black hole plays a role of some kind of heat bath with this Hawking temperature. The point is this Hawking temperature also proportional to h bar. So in classical mechanics, this temperature is 0. So this is perfectly consistent with our understanding of black hole. And so this story is very similar to this chaos story. So at the classical level, the temperature is 0. But once we turn on quantum effect, and if we believe this inequality, this temperature is bounded from below. It means somehow it acquires some kind of temperature.
Probably you mean there is some large n in the system, right? Because I think if you have a single particle type physics, then your h bar has to be going to 0. So
In this talk, indeed, even in some single particle, we will see some kind of thermodynamics. Maybe
because this quantum correction.
Usually it scale with n, but here in this talk, I will not consider that limit. Even what I will show is consider some single particle motion, like this kind of motion, and we will see some kind of thermal correction that I will explain later. So,
I just have a small comment on this, probably related to Alexios's question. So this Lyapunov exponent is not what people calculate in classical mechanics. So there is some change, different.
In quantum mechanics, yes, I agree. But yeah, I will show that this. So I will explain some kind of some time evolution of the system, and we will see some kind of emergence of thermodynamics. But this occurs within this LFS time. So then the meaning of this Lyapunov in classical mechanics would be valid. So.
No, but I think there is a totally different, because this Lyapunov exponent quantifies chaos in a local phase space. And in classical mechanics, what people call as Lyapunov exponent is like long time average.
That's point I will comment later.
So can you explain perhaps what you mean by turn on quantum correction? I mean, so you're comparing a classical system to what?
To some semi-classical system.
To a semi-classical system in which way? I mean, so the classical system, you have some Poisson brackets or whatever, and you specify some initial conditions that gives you a Lyapunov exponent. So now that evolution you compare to what?
Oh, you mean compared. Oh yeah, so yeah, I will use some WKP. Yeah. So anyway, so these are very rough sketch, and I will show some concrete calculation. And also, so what I like to explain today is mainly three points. So first is indeed in this kind of first of all, this doesn't say this kind of things. What they consider is finite temperature system from the beginning and fully some quantum system. So then if this is true, then that sounds interesting. I mean, such kind of classical system behave as a black hole system. So that is the reason why I'm interested in this system. But since Maridas didn't consider in this way, so today I like to consider whether in this way and whether we can see some kind of emergence of thermodynamics in this kind of system. And indeed, I will show that in some, not a general system, but in some chaotic system, maybe this kind of emergence of thermodynamics will appear. And so this is the first point I like to explain. And the next, I also briefly mention some kind of, even in this, this is inequality, but this inequality may be saturated even in some integrable system, and this is some second point. And finally, I will explain some connection to this emergence of thermodynamics and acoustic Hawking radiation in free fermion system. And this is some concrete example that this kind of thermodynamics is related to some kind of black hole physics. So this is okay, so first I briefly explain the emergence of this thermodynamical behavior in chaotic systems. So here, this is some, as I said, it is very difficult to discuss chaos in general. So I consider some some specific example. So if you open any textbook of chaos, you will see this kind of picture, and this explains some kind of mechanism for chaos. And there are two important ingredients in this kind of chaotic motion. One is hyperbolic fixed point in this picture, this point. And around this point, this line is particle trajectory, and around this point, a particle move like this. And this is called a hyperbolic fixed point. And another point is some kind of disturbance of this motion. And then by repeating this kind of complicated stuff, then we will see chaotic motion. And one typical example which I am in mind in this talk is damped-driven pendulum motion. So this is a standard pendulum problem, and this is a motion of the pendulum in phase space. This is momentum, and this is momentum, and this is position. So, for example, here I haven't turning on this damping and some external force. This is just a purely pendulum motion. So you see this circular motion corresponds to this standard oscillation of the pendulum, and this motion corresponds to this rotation motion of this pendulum. I don't know, sorry. This is some, sorry, this is some, yeah, I haven't checked. So, sorry, I couldn't. If anyone knows the answer, right, that's the point. Yeah, but, yeah. But so, yeah.
Without damping, you cannot have fixed point dynamics. I think that's you cannot have fixed point type dynamics without damping.
Oh, yeah, or maybe that. Maybe, yeah. So this is a result, and this. It shows some chaotic motion. And the point is, so here, this hyperbolic fixed point exists in this classical, in this phase space trajectories. And so indeed, this kind of point is important to see some kind of chaotic motion. And so today I like to show that this hyperbolic fixed point play a very important role to see some kind of thermal behavior. And to understand this motion, we can consider the following simple model. So the particle motion near this hyperbolic fixed point can be approximately described by this inverse harmonic potential problem. So this is a phase space trajectory of particles in this inverse harmonic potential, and here is a hyperbolic fixed point. So we can use this simple model as the effective theory of chaos around this point. So from now, we focus on some dynamics of particles in this inverse harmonic potential, and particularly I like to consider what is going on in semi-classical regime. Okay, so this is a very simple question, and even undergraduate student or maybe even high school student can answer. So we have now inverse harmonic potential and consider particle motion in this potential. So here I consider this potential, alpha is some constant, and then the motion is very simple. So if energy is positive, then this particle just goes through this potential, and if the energy is negative, this particle just reflected by potential. So it's very simple. And we can also solve equation motion, of course, and this is the equation motion, and the result is given by this one. So here, this C1 and C2 are constant depending on some initial condition. And the point is this particle motion depends on time exponentially. So it means we can define Lyapunov exponent, that is this one. This is just a coefficient of this part. So this is one reason this hyperbolic fixed point is important in chaotic motion, because it will explain some kind of exponential growth of the system. So, so anyway, so this is a very simple problem. And now I consider some semi-classical case. So So in semi-classical regime, the particle motion is changed. That is also very simple. So even if the energy of the particle is negative, this particle can penetrate this potential through quantum tunneling. And similarly, even if the energy is positive, sometimes through this quantum reflection, particles are reflected by this potential and going back to this way. So this is also very simple dynamics. And by using WKB approximation, in this case, we can exactly calculate this tunneling ratio through standard quantum mechanical calculation, and we obtain this ratio. So this is some tunneling ratio, and this one is the probability taking classical trajectory, and this exponential one is the probability for this tunneling. And similarly, this is for quantum reflection. This one is for classical trajectory, and this classical means going the probability for going this way, and sometimes quantum mechanically this particle reflected to this way by this probability. And here beta L is some constant related to Lyapunov exponent in this way, and E is the energy of the particle. So here, this is interesting enough because this exponential, so this it depends on the energy in this exponential way, and it's similar to the Boltzmann factor of thermodynamics. And so this is the reason why I use this beta for this coefficient. And quite interestingly, this beta is related.
Sorry, but there's no temperature in the problem. I mean, so you...
No. So it's just a coefficient, and I wrote so this is just a probability, and I wrote this probability by using this beta and T, and of course this is not the temperature. This is just a tunneling ratio, and but here this is suggestive in a sense that this if we interpreted this beta as temperature, inverse temperature, then we have this relation. This lambda is this Lyapunov, and of course this tunneling is related to this shape of this potential, and so this we have this relation, and this relation saturates this bound. So this is a very simple model, but it seems this model somehow capture this connection, and of course, this is.
Well, why do you say that? I mean, because your whole argument hinges on the fact that you interpret this beta L as a temperature, as an inverse temperature. But so why?
Okay, so that I'll explain. Yeah. So of course, this is just a tunneling relation. So here, it looks nothing to do with thermodynamics. It's just a probability. But we can consider in the following way. This is some phase space version of this motion. Classically, it's going in this way. So this is a positive energy particle. It goes through the potential, and sometimes it's going back through quantum effect. And this is a negative energy particle. So classically, it's just to go and back, but quantum mechanically, sometimes tunneling occurs in this way. And okay, so now I like to explain for the connection to some interpretation of thermodynamics. So in order to see some connection to thermodynamics, I like to consider the following question. So suppose every particles are coming from the left region, and particles scattered by this potential, and consider the energy transfer by this quantum effect. So we can ask the following question. So how much energy is transferred by this kind of quantum effect comparing with the classical motion? So then the answer is as follows. So suppose we consider this positive energy particle, then this is reflected and going in this way. So it means if this quantum reflection occurs, the energy in this left region increases because it carries positive energy. And this occurs with this probability. And similarly, if we consider a negative energy particle, and then sometimes this tunneling occurs, and then the energy is transferred to this left region. but this one carries negative energy because this is negative particle. It means through this tunneling, the energy in this left region increase because this one carry negative energy. So it means negative energy in this left region decrease, which means the energy in this region increase. Or we can regard this is a kind of Hall creation. I mean, if particle disappear into this direction, and this it means it can be regarded as a kind of Hall which carries positive energy, and the probability is this ratio, and this is just a tunneling relation, but this can be rewrite in this way. So here is negative quantity, and so this minus is positive quantity. So we can combine these two equations in this way. So in both cases, in this positive energy and negative energy, if some quantum tunneling or reflection occurs, the energy in this left region increases, and the probability is given by this Boltzmann-like factor. So in this sense, we can regard this is so if we consider only this left region, this is very similar to thermal excitation. So the energy in this left region increases by this positive quantity, and the probability is given by this exponential factor. So now the analog to thermodynamics is very clear. So of course, this is simple tunneling process. Even undergraduate student can understand, but it can be interpreted as some kind of thermal excitation in the sense that energy in this region increases by this probability. And so this picture can be summarized in this single picture. So if particles are coming to this potential and scattering somehow, and then this quantum effect make some excess of energy in this left region, and it occurs with this Boltzmann-like probability. And this is very similar to thermal excitation of a two-level system. So here, this is the excess of the energy, and this is the probability. And if a particle just goes through this classical trajectory, so if a particle take this classical trajectory, the energy is a kind of zero, because here I evaluate the excess of the energy over a classical process. So if this particle take classical process, the energy is the excess of the energy is zero, and it occurs with these probabilities. And if this particle take this quantum trajectory with this probability, the excess is given by this one. So in this way, this kind of energy transfer can be interpreted as thermal excitation. And of course, this is just quantum mechanics and not nothing to do with real thermodynamics, but some kind of this can be interpreted as thermal excitation. So this is my point. So of course, this is a completely unitary process. But as far as we just looking at some energy in this region, this can be regarded as a thermodynamics. And okay, go ahead. Yeah. Yeah. So just yeah. So here, yeah, that's just yeah. That's true. But just yeah. If you consider just a single particle, then the possibility is taking classical over quantum. So just two possibilities. So in that sense, I call it a two-level system. But of course, there are a lot of particles, and the energy depends on some each particle. So then it will be continuous. So yeah. In some sense, so when I discuss the connection to this acoustic Hawking radiation, then yeah. Oh yeah, that's true. That's true. Yeah. Information about this, yeah, right. Yeah. Yeah, so that's a point. So this is, yeah, so this is a kind of model of a black hole or acoustic Hawking radiation. And suppose this point is, suppose we regard this point as a kind of a horizon and we ignore what is going on in this right region, then it's really like a summer excitation. And in black hole case, it physically realized, and in acoustic Hawking radiation case, if we focus on dynamics of phonon, it realizes. So then we can justify ignoring this right region. So, okay, so any other question? Okay, so then, yeah, so here several remarks, maybe some of them related to some several questions you guys asked. And so the first one is about Ehrenfest time. So it is true in general in full quantum mechanics, the definition of the Lyapunov exponent in classical mechanism is subtle. But this kind of scattering process will occur within this Ehrenfest time. So then this kind of Lyapunov may be meaningful. So then we can avoid using some OTOC or some stuff to define this kind of Lyapunov. And another remark is about integrability. So in this model, I just consider inverse harmonic potential, and it means and this motion is yeah, as you can see, we can solve it exactly. So it's integrable. But this model is integrable, but still we can define Lyapunov in some trivial way. And if we regard this kind of effect as a summer effect, then it saturates this bound. So this is, I think this is interesting because this is not, it seems this mechanism itself is nothing to do with chaos. Just inverse harmonic oscillator can explain some this kind of saturation. And so, yeah, it's not clear whether this relation is related to some maximal chaos or fast scramble. I mean, even such kind of simple motion shows this kind of relation. And also related to this integrability, this inverse harmonic potential is also used in Shih-Coleman matrix model in string theory, and that is also integrable. But so if we consider instead of this bunch of particles, but infinite number of particles, then we can consider some non-critical string theory, and we can consider this as, we can regard this model also saturate this bound. So even integrable system, in this sense, I mean, if we interpreted this kind of phenomena as real thermodynamics, then it saturates this bound. And of course, this is quantum mechanics, and it's subtle to interpret this as real thermodynamics. But as I said, in black hole system, we do some similar stuff. So maybe it's not bad to interpret this as a thermodynamical system. Okay, so there's another comment. This is about some kind of universality. So here I just consider inverse harmonic potential, but we can consider various potentials. And even these cases, we can see similar argument. And since this kind of tunneling occurs around this energy close to zero, so independent of the detail of the potential, this kind of thermal emission will occur. But then this saturation of the Lyapunov is subtle because if this potential is not the inverse harmonic potential, then the time evolution would be different. So if we define this Lyapunov for very short time, then we can argue this kind of, we can say this Lyapunov saturates this bound. But if the potential is something like this, and if we consider some long time behavior, maybe the connection between Lyapunov and temperature will be changed. And related to this, if we consider real chaotic system, and then the Lyapunov around this hyperbolic fixed point and the Lyapunov of the whole system would be different. So in this sense, so in this kind of approach, it is difficult to understand this inequality. Maybe it's related to kind of what is a natural model of chaos, and for some model maybe this kind of inequality could be argued, but in general, in this kind of approach, it is difficult to understand this inequality. Okay, so anyway, so this is some remarks, and yeah. Yeah. Them we will not get this kind of behavior, and it's of course this tunneling would be changed, so the interpretation of this thermodynamics will fail. First of all, it's not this kind of probability doesn't appear in X2 for potential. Then I cannot interpret this. That was Boltzmann factor. So same story would be completely changed.
Yeah, I have a stupid question. I mean, so at very short times, you actually don't have an exponential bound, right? Because then the two exponentials are of the same order. Yeah. So you have the exponential growth in the regime where the exponential is really, really, really large.
Yeah.
Yeah. And so then X is large. And then supposedly you're no longer close to your crossing point.
Sorry, I missed the point of the question.
Okay. So you have the exponential growth in the regime where X itself is large, supposedly.
Yeah.
Yeah. Because before the two terms are of the same order. Yeah, so the
term means which term and which term?
C1 and C2 terms. Yeah. So you have a lower cutoff on the time before which you cannot see exponential growth.
Yeah.
Yeah.
From this.
On the other hand, when X itself becomes large, then supposedly your quadratic approximation is unreasonable.
Oh yeah, that's true. So yeah, this is a kind of convention, but. I guess the point would be the particular has, so the tunneling occurs very close to this trajectory, and very close to this trajectory, it would be, I suppose the one of the, so this.
So in harmonic oscillators, there is a time scale which is given by omega oscillator, and there is h bar over omega square root, which is oscillator length. So if h bar is small, then in principle you can have it's already very small, but the length is still not very large. You can play with this.
Okay, thanks for comment. Okay, so maybe yeah.
I have some comment which might be of interest to you, that if you actually solve the problem with inverse harmonic oscillator exactly, not semi-classically.
Sorry, for our quantum mechanics? Sorry.
If you take inverted harmonic oscillator and solve the problem exactly, not semi-classically, as you did, then you'll get Fermi distribution.
Yes, that's yes.
Just a comment.
Yeah, but that is this is sorry. This is exact result, and that is Fermi Dirac. And if we rewrite that relation to this way, I mean, so I normalize this probability so that this classical trajectory is 1, and this so then it becomes this Boltzmann weight. But if we normalize this incoming wave as 1, then we got Fermi Dirac. So this is indeed the exact result. Okay, so then I like to move to this discussion on this connection to acoustic Hawking radiation. So first, I briefly review what is acoustic Hawking radiation. So this is proposed by Andrew. So what he considered is the following setup. So we consider one nozzle which becoming narrow and narrow in this way. And suppose we inject some fluid from the left to right. Then the speed of the fluid increasing along this nozzle. And then maybe the speed of flow exceeds the speed of sonic. And there some supersonic region appear. And in this left region would be subsonic. And suppose this dotted line is the border between this supersonic region and the subsonic region. So then if you focus on the dynamics of phonon, and then, so here the phonon cannot propagate into this region because the speed of sound is, the speed of fluid itself is faster than the speed of sound. So every phonon, so every mode goes in this right way, and any mode can propagate to this way. So it means for this phonon, this boundary between subsonic region and supersonic region is a kind of event horizon. And the phonon in this region is causally disconnected to this region. So then once we quantize this phonon, then similar to the calculation of the Hawking radiation, we will see some kind of energy transfer occurs, and that it depends on some, it obeys some kind of thermal distribution. So this is called acoustic Hawking radiation, and the dynamics is almost the same to the standard of Hawking radiation in black hole. Okay, so now so we can consider the following setup. So in the first part, we consider this kind of particle scattering problem. And suppose we consider infinite number of fermions as a free fermions and occupy the Fermi energy in this way. And the particle is always coming from the left to right. So then this can be regarded as a fluid, and then we have a chance to consider some acoustic Hawking radiation by using this quantum mechanics. And indeed, this is considered by this person, Gino Banacci first, and I also do some calculation. And then, so if you remember the first part of my talk, if particles are some coming from the left to right, and then through quantum effect, the energy transfer occur, and the energy in this left region increases, comparing with this classical motion. And so some energy flows occur in this way through quantum mechanics. And since now we are considering fermions, this thermal emission obeys Fermi-Dirac distribution, and some kind of thermodynamics will appear. And since this system is equivalent to fluid system, and we can show that if these fermions occupy from the ground state to this state, so here I put some suitable boundaries so that the fermions are quantized suitably, and then we can see that the speed of we can show that this region is supersonic and this region is subsonic. I'll explain later, but because of that, if we quantize phonon in this setup, we will see acoustic Hawking radiation. And I will show that this quantity and this quantity are identical. So from the picture, that is trivial, but calculation is a bit non-trivial. But what I like to claim is the thermal emission in this quantum mechanics is equivalent to this thermal emission in acoustic Hawking radiation. So it means since this phenomena is related to some thermal emission in this hyperbolic fixed point, so in this sense, this kind of emergence of thermodynamics is related to Hawking radiation. That's I want to claim. Okay, so I briefly explain the details, but it's very simple. So this is a picture of the quantum mechanics. So so then it is easy to calculate this energy flow by using quantum mechanics. So the result is just this one. This is the tunneling probability, and this is a kind of density of state in this system, and this is for energy for this positive energy particle. And then by summing up, we obtain this energy flux at some, this is some energy density at position x. And this is just a quantum mechanics. And so then we can do the same, the corresponding calculation by using fluid mechanics. So here I like to skip the detail and briefly mention why this region is supersonic and this region is subsonic. And we can understand why this is supersonic and this is subsonic in the following way. So as I said, I occupied fermion from the ground state to certain energy level, and that is this line. And so this is this is a fermion droplet in phase space. So in this triangular region, the particle in this region represents the particle in this negative energy, which just go to this potential and reflected by potential. And this region represents the particle for this positive energy. So the particle is coming and goes through the potential. So in this picture, this particle corresponds to these particles. And since this is a kind of ground state, and the phonon is given by some fluctuation of this Fermi surface. So that is like this. So if the surface is fluctuate, then from this particle motion, we can understand how this fluctuation propagate. So if the Fermi surface in this region fluctuated, the fluctuation propagates always in this way, because the particle is moving in this way. And if the Fermi surface of this region fluctuate, then particle go to this way, so this fluctuation propagate in this way. And if this region is fluctuate, it goes in this way. So it means the propagation of the phonon is as follows. So in this region, so this phonon and this phonon go in this right way, but in this left region, this phonon go to right way, and this phonon go to left way. So it means the direction of the propagation of phonon is different in this case. So in this region or in this region, both phonon propagate in this way, and in this left region it go in both ways. So it means this region is supersonic because no phonon can propagate to left way, and this region is subsonic since there is left mover and right mover. So anyway, so just looking at the fluctuation of this surface, then we can regard this is supersonic and this is subsonic. So then, okay, so then if we quantize this phonon, indeed we can show that some kind of acoustic Hawking radiation occurs. This is just some simple quantum field theory and some Bogoliov transformation. We can show exactly the same flux that does appear in this region. So we can see the agreement between this quantum mechanics and this fluid mechanics. And from the construction, this agreement is very natural. But one interesting point is these two descriptions are very different. So I mean, so one is just quantum mechanics and another is phonon. Or we can say this model is microscopic and this is macroscopic. So these two descriptions are very different, but still we can obtain some same result. It's very natural, but I think particularly this kind of new way of understanding of this Hawking radiation may provide us some deeper understanding of Hawking radiation. So for example, this statistics is different. The phonon is boson, and here this fermions are fermion, and we use quantum field theory, and here quantum mechanics. And one interesting point for me is whenever we calculate this Hawking radiation, so we need to choose some suitable vacuum. And in this case, we have to choose so-called under vacuum. And so the related point in this quantum mechanics picture is some choice of boundary conditions incoming particles. And somehow very natural boundary condition provide us some this simple picture. So somehow this, there is some connection between under vacuum and this some boundary condition with the particles. Okay, so anyway, so in this way, so we can understand this kind of some kind of emergence of thermodynamics is related to some black hole physics. Okay, so let me summarize. So we have seen that if we naively believe this inequality proposed by Morita, Schenker, Stanford, then it may mean some kind of emergence of thermodynamics in classical chaotic system. And we've argued that if we focus on some dynamics near hyperbolic fixed point, then such kind of factor does appear, and it may be interpreted as some kind of thermal excitation. And of course, this is a matter of interpretation, but by using this setup, we can indeed construct Hawking radiation. So in this sense, this may be, this kind of motion may be related to this kind of inequality or some kind of first scrambler or maximal chaos. Although this is integrable. Okay, so I'm stop here. Thank you.
What about just the linear potentials? I think that some part of this physics is due to the unbounded spectrum in your...
Yeah, in this case, unbounded. So I put some cutoff by...
Yeah, but if you just take the linear
potential, you mean this kind of cusp phase. So for these things, so existence of this tip of the potential is important. So if we just consider linear one, then no tunneling occur, and just every both classical and quantum particle are reflected by the potential. So I think
that will suppress, pull the Lyapunov exponent below the bound, or it will.
So first of all, in linear case, there will be no Lyapunov, isn't it? In linear case, it's just a constant acceleration. So x goes as some t square or something, right? Yeah. So, yeah.
Yeah.
So, it's on. So, so in acoustic Hawking radiation, there's this picture of a river, okay, a strongly flowing river, and a fish which has a velocity more than that of the river, that can go ahead, and any fish which has less than that, so that cannot that cannot go beyond a certain barrier, spatial barrier. So here, is it like each of these energy surfaces, they are like, you're thinking of these as some streamlines and these little blips like the fish in the river, or what? I mean, is it?
Yeah, yeah.
I mean, in the sense that who is exceeding what? Energy. So you're saying that the energy of the blip, it's exceeding what exactly? What is the critical? I mean, it's just up there. You're saying it's on the upper hyperbola, and then it can go only one way.
Yeah, but if there's very big oscillation, so that this one exceeds this point,
right,
then it can go this way.
Okay, and supersonic would mean that it's just too high up. Is that right?
Yeah, and again, if we consider very large deviation like this and exceed this line, it can propagate this way. So if you have very tough fish, that is given by this description. So it's huge deviation from this configuration, which can go in this way.
I see.
So,
Okay,
so this causality is just for very small fluctuation.
I see. Okay, thanks.
More questions? Okay, if not, let's thank Takeshi again.